So this lecture is about heap sort. So first of all, we must know that what exactly is heap sort and what shall be the complexity of its running time. So the running time complexity for the heap sort is big O n log n, which is very much similar to merge sort. The second thing is the sorting in place. Only a constant number of array elements are sorted outside the input array at any time. So there are two different structures. One is the array, the other one is the tree. So we can sort the elements outside the input array at any time, which is very much similar to the insertion sort. So what exactly is heap? Heap is a data structure which is used to manage information during the execution of the algorithm, and this data structure is basically based on tree, and the tree which contains two elements means it is supposed to be a binary tree, and this binary tree should be complete. So usually heap sort or heap technique is used for an efficient priority queue. So how we can see in terms of tree structure. So for binary tree with the height h, we can say that every node contains two children in full. So we call it a perfect binary or complete binary tree. So here you can see that the root is h is equal to 0 when the root has no child. When the height increases by 1, so it contains two equal child, and similarly as we move or the increases the levels of the tree, every node contains two children. That is the full or complete binary tree. So if some of the tree is not having the elements, then it should not, you can say that complete binary tree, all leaves on level h are as far left as possible. So whenever we are increasing up the level, we are basically putting up the nodes on the left hand side first and then the right hand side, and so on. So here you can see that in level h1, so we are having the node on the left hand side, then the right hand side. Similarly, when h is equal to the first one developed by the, you can say on the left hand side, then the left hand side is producing the another one, and it creates the right hand side and the left side of the other element, and so on. So this is how it moves forward. So every node contains two childs, and the child in the left should complete first. So this is how if the height is 3, so it comes to, so you can see that in every step every level should complete first. So the level 1 complete first, then the level 2 and the level 3. Whenever we are completing the level, the element should be on the left hand side first, then the right hand side element comes next. In the heap we are having two different properties. The very first thing, it should be a complete binary tree, and the second thing, that there must be a relationship between the parent node and the children nodes. So what kind of relation it can acquire? One is known as minimum heap, the other one is known as maximum heap. If the parent value is smaller than its children's value, we call it minimum heap, or if the parent value is greater than or equal to the value of the children's nodes, we call it maximum heap. So we can see over here that there is a heap example as well as there is non-heap example. In heap side you can see that 5 is either equal to 5 or 5 is smaller than 45, so we call it minimum heap. And we can also reverse it into a maximum heap fashion. So here 5 is smaller than 6, 5 is as well as smaller than 22, and 6 is smaller than 25. Where on the other side, which is non-heap, 5 is smaller than 8, fine, but 8 is not smaller than 6, so it's a mixed combination of lesser and greater values. So we call it, this is non-heap tree. So binary heap, an array object that can be viewed as nearly complete binary tree. So binary means two nodes. So our heap is always a binary tree in which you can say that the tree is completely filled with all the levels except possibly the lowest, which is the filled with from the left hand side. If we are if reach to the last node which is producing leaves, so the left leaf should be filled first and then the right one. A maximum heap, so if we are having an array of different values, so how we can fill these values to the maximum heap. So what do we need? We need to put the max value of the first element as the node, and then we choose the second one and the third one. So we need to keep the relationship between the nodes, whether we are creating the maximum heap or the minimum heap. So here if we placed 16 at index 1, which is basically index 1, and then we placed on the left hand side the index 2 value, which is 14, and the relationship is that the 16 is greater than 14, fine. Then the index 3 value, which is at 3, it's again perfect, there is no issue, 16 is greater than 10. Then we need to read index number 4 value, which should come at the left hand side of the 14. So here it comes, and then 7 comes on the right hand side, which is again smaller than 14. After 7 we cannot jump down, so we need to jump to the node which is basically 10. So 9 is smaller than 10, fine. Then 3, which is smaller than 10, it is also perfect. And then you can say that 2, it will belongs to 8, and 4 belongs to 8 as well, because both are lesser than 8. So we need to fill the left hand side first rather than we move towards right hand side, and 1 is less than 10. So this is how we can index the values and create a maximum heap tree. So this is the relationship between a tree and the array, you can say. So length and the heap size. So how we can calculate the heap size or the length? The length of the array is as same as the length of the heap. So heap contains all the elements, and element must be as same as the elements of the array, so both are same, and in this case the value is 10. What shall be the fundamental procedure, or you can say the basic procedure, in order to establish the heap? Here we can say that the given index of I of the node, that indices of its parent, left child and right child, and can be computed simply. For example, a1 is the root of the tree, so parent I number 1 written I divided by 2. So how we can identify the value of parent? So parent is basically splitting into 2, and how we can identify the child? The child is basically a member of the parent, so it's 2 into I, and the next element which is on the right hand side must be 2I plus 1. So how we can identify the value? So if we need to identify, for example, 8, so how we can identify the value of elements which is being associated with the 8? So the index of 8 is 4. So how we can identify the child index? So on the left hand side it must be 2 into I. So if the index value of 8 is 4, then its first child index value must be 8, and the next child value must be 2I plus 1, that is 8 plus 1. So this is how we can easily compute the tree with the help of the formula. So we can easily jump from one element to the another element in order to represent heap tree. So because in computers we are not creating trees, we technically create arrays, but we need to make the relationship between different elements so it can produce a perfect heap tree. What shall be the basic operations? There are 3 basic operations. Left procedure that computes the leftmost value, the right procedure that quickly computes the rightmost and the parent value, which computes the floor value by shifting the I, that is the index, right one bit position. So this is how it computes the elements. This is the heap computation. Parent I is the index. So for example, if we are talking about 10 having the index 3, so what shall be the parent value? So 3 divided by 2, it's 1.5, and it is the lower case, so it becomes 1. So this is the 1 value. So how can I get the next value? Of the left hand side, the I is 3, so the left child must be 2 into I, that is 6. So 3 is connected with 6, and the rightmost child is connected as 7, because 2I plus 1. So this is how it connects with each other. So this is how we can calculate the values of parent and left child and the right child. What are the properties of heap? The property that the values in the node must satisfy, that the heap should contain either a max heap fashion or the minimum heap fashion. So there are the two different types, minimum and max heaps. Max heaps means the node must contain the children having the least value, and minimum heap means the parent contains the minimum value in comparison with the child node. Heap height means the height of the node in a heap, the number of edges on the longest simple downward path. So in this case 1 2 3, so the height of the heap is 3 because it is the number of edges on the longest branch. So for every node we can calculate its height. So if I am standing at 4, so the maximum extending edge is simply 1, so the height of 4 is 1. For the whole heap, the height is 3. So the height of the heap of n element is equal to theta log of n. So we can calculate the complexity as well. Heap procedures, max heapify, that how we can calculate the maximum heap, maintains the property of max heap tree. Build max heap, how we can, this the way we can produce heap tree, and then finally sorts an array in a place with the help of heap sorting approach. So if you want to maintain the heap property, we need to see that how we are taking the values out of the heap. Whenever we are moving the values of heap, we must know that the heap should remain in its original form. That is the condition of the heap, whether it is max or minimum. So for example, in this case we are having 4 over here, which is not heap, so we need to move this 4. So we need to compare 4 with 14 and 7. So how we can move this 4? So the 4 goes either this way or that way, so we always move it to the left hand side. The 14 is replaced with 4, because if we replace 4 with 7, so 7 is again less than 14. So we need to compare these elements, which one is the highest one. We replace the 4 value with the highest one. So 14 is replaced by 4, and when the 4 comes on 14's positions, then 4 is still smaller than 8, but it's greater than 2. So we need to replace 4 by 8. So this is the heap in its final form. So this technique, this procedure is known as maintaining the heap property. So that is the example which we were talking about, that 4 is less than 14, and this is how it moves towards there. And this is the algorithm which is already available in the book, so you can easily identify that how we can implement heapify. Running time of maximum heap, to find the largest among it is a constant value, so the theta value will be 1. So in our case, according to the master's theorem, then we can calculate the complexity of max Heapify algorithm as big O log n. So you guys have already been through the master's algorithm, so here I'm not going to discuss how we can uh, implement master's algorithm, but if you are implementing this logic, then you will get the value of big O log n. And finally, this is the example which is taken from the book. Max heap, how we can build up the max heap value. So if this is the case and this array is not in its sorted fashion, so you can see that the element 4, 1, 3, 2, 16, 9, 10, 14, 8 and 7. So initially we put 4 on the top, we take 1 and 3, both are fine, and then 2 should comes at this position, and then there is a 16. So in this relationship, the 16, when we place the second child, we find out that 1 is technically less than 2 as well as 16. So we need to eliminate this element accordingly. So we need to check step by step. So here you can see that the 16 has been replaced both 14 and 17. So whenever we jump down, we need to move the value. We cannot leave the value as it is. So in this case, 1, 2 and 16 is over there. So the first value is 2, which is greater than 1. So we need to see that how we can fix this value. So if 2 is having the nodes which are greater than 2, so we need to eliminate the bigger value among the child. So we need to resolve things from the bottom. So here 14 comes on the top. Then we need to see whether the 16 is having the relationship with 7, and what kind of relationship is this. So 16 is greater than 7, it's fine. So we jumped 16 on the top and 1 over there. But if we compare 1 with 7, we need to replace 1 with 7. So 1 comes down and 7 comes up. So here 1 comes down and 7 comes up. So the track is going like this. On the other side, we can see the nodes are very smaller in size, the height is very low. So 3 compares with 9 and 10. So we simply identifies the greatest value among these 3 and put on the top. So the 10 comes on the top. So this is how we creates max heap structure with the help of any given array. And here is the final version of your max heap. So the correctness means that we need to check all the time whether the heap function calculates the heapify value at each and every node or not. So whenever we move a node, we need to check whether the moving node is perfectly fit in according to the heap structure or not. And when it completes all the indexes or all the nodes according to the heap structure, the algorithm must terminate. This is same as building up the heap. So we need to build up the heap and then put the maximum element a1 to an. So step by step we pull out the value from the top and then again heapify the whole tree. Then we always know that the maximum value comes on the top as the root, so we always take the value from the root. So whenever we take the value from the node, the root should be filled up with one of the element which comes from the child node, that is at the bottom. So if we are taking out 16, so after 16 the value must be 14 and then 10 and then 8, 7, 9, 3, 2, 4, 1. So if we are placing in this order, you can see there are some values which are in sorted fashion, but not all of them. So how we can move these values? So first we eliminate 16. So we eliminate 16 first, and when we eliminate 16, the 14 comes on the top and who takes the value of 2, it's 8. So every node is working with the help of heapify structure. So if we are taking 16 out, so who is bigger than 14 and 10? 14 is the bigger one, so we replace 16 by 14. And how we can replace the fill in the value of 14? We need to identify 8 and 7. So which one is bigger? 8 is bigger, so we can put the 8 value over there. So this is how 8 comes over here, and then 4 comes instead of 8, and 4 takes 1 from 9, because all the values must be filled on the left hand side first, rather moving on the right hand side. So every element, so in this situation, if I am moving 4 over there, so there is 1 less of the node, so I need to take the node from the other side. So 1 comes from 7 and it jumps toward 4. And similarly, if we are moving the values from always top and always makes the tree according to the heap structure, the final structure or final indexes will take the values in certain orders, and that order shall be either ascending or descending. If we are placing 16 at the end of the array, it will be an ascending. If we place 16 at the first value or the 0 index, the array must be descending order. Priority queues are those queues which are having the data structure of maintaining as elements with the associated value of key, which is basically either maximum or minimum. So normally priority queues takes the maximum value. So with the help of heap, we can have always the highest value on the top node. So this is how we use max heap structure in order to implement priority queues. And this is how we can extract the element which is on the top. It is always max. And these are the insertion and heap increase key. This is how we can implement or insert an element to a heap value. So that's all for the heap sort. Thank you very much.